In this video, we're going to look at reactions as acids. So we're going to look at the acidic nature of carboxylic acids. If something willingly loses a H+, then it is considered to be an acid. The OH group is polar enough that a H+ can be lost. Alcohols have a low tendency to lose H+, less than water, so they only react with very reactive metals. Carboxylic acids, on the other hand, are much more reactive. That's due to the inductive effect in the COOH group. We'll look at that a little more in a little while. Carboxylate ion is very stable. That's due to the electron delocalization, as can be seen in benzene as well. And the stability is driving force behind losing the H+. Okay, so reaction as acids. We have alcohol and a reactive metal. Alcohol and sodium form sodium salt and hydrogen. That's what we're going to be looking at in this video mainly. And then we have reaction of acids. So we have an acid with magnesium will form magnesium salt and hydrogen. An acid and NaOH will form sodium salt and water. And an acid and sodium carbonate will form sodium salt, carbon dioxide, and water. So if we concentrate on our reaction of an alcohol with sodium, okay, ethanol reacts with sodium to form sodium ethoxide and hydrogen. So we have Na plus C2 H5OH, and that gives us C2 and plus hydrogen as well. Okay, in order to balance that, then we need 2, 2, and 2. So this is our sodium. This is ethanol. This is sodium ethoxide. And then we have hydrogen also at the end. Okay, so we can see almost it's similar to one of our substitution reactions maybe, because this hydrogen here is replaced with a sodium. So then here where this sodium is, that is where the hydrogen was, and the two hydrogens that were over here are now separate from it. So this ethanol here, we can say it behaves as an acid because it loses H+. Okay, alcohols they're actually much weaker acids, even than water. So they only behave as an acid in the presence of a reactive metal. So in this case, our reactive metal is our sodium. So that is our reaction of ethanol and sodium, so an alcohol and a metal. Okay, if you want to look at reaction of acids, okay, there's lots of material out there on the internet, and there's also lots in your textbook as well about them reactions. Okay, they're not the most complicated ones we're going to look at, so not going to include them in this video for now. What we will look at is we're going to look at the acidic nature we're going to look at the acidic nature of carboxylic acids. Okay, so first thing we're going to look at is the inductive effect. What the inductive effect means is that if we look at the structure of a carboxylic acid, O double bond C to our side chain, and we have our OH group. This double bond, this C double bonded to oxygen, that draws electrons away from the OH part of the molecule. So electrons are attracted, but they draw electrons away from that part. That means that this H plus isn't as tightly bound. It doesn't take as much energy for that to be lost. Okay, so the proton there can be lost much more easily due to that inductive effect. The second thing we're going to look at is the stability of the carboxylate ion. Okay, so that is when this H, this proton, has actually been lost. Then you have a carboxylate ion. So if we look at the stability of it, it is stable because it has resonant structures. Okay, so one resonant structure is this. Okay, another resonant structure can be this. Okay, so it doesn't matter. The double bond can be the top one up here, or it can be bottom down here. Because you have those resonant structures, there's an even spread of charge between these three molecules due to those resonant structures. So there's an even spread of negative charge throughout them. So we can have that the structure that appears anyway is this. And throughout here you have a negative charge. Okay, so there's an even spread of charge due to that resonant hybrid structure. Even spread of charge through those three atoms.